Hello, in this video we are going to be looking at concavity and points of inflection. Specifically, we are interested in knowing what the second derivative tells us about a function. So let's look at the definition of concavity. A function is going to be considered concave up if your second derivative is positive. Now, this has a couple of implications. One implication, remember your second derivative is the rate of change of your first derivative. Your first derivative tells you slopes of tangent lines, so if the rate of change of the slopes of the tangent lines is positive, meaning that slopes of tangent lines increase over an interval, this would mean that your second derivative is positive, meaning that the function is concave up. So we look at a graph. Our first point that we pick on, the slope of the tangent line is some negative number. Maybe this is like a -1. And then you move over and you find another point and you check its slope of its tangent line. Here we have a positive slope of a tangent line. It would look to me like this is maybe like 1/2 or 1/3. So we see that we increased from a negative number to a positive number, meaning that the graph is concave up. Now, visually speaking, when you look at a graph, you can tell it's concave up if it looks kind of like a upward-facing bowl, or really if it looks like any part of an upward-facing bowl. So if you have a part of a graph that looks like this, ignore the left side. If you have a part that looks like the right side, if it looks like an upward-facing bowl, we are concave up. Or if you just focus in on the left side, if it looks like an upward-facing bowl, we are concave up. We also define another type of concavity. A function is going to be concave down if the second derivative is negative. So this would mean that the slopes of tangent lines would have to decrease over the interval. We go from positive slopes to negative slopes. And then it should look like the bowl is opening down in order for the function to be concave down. So let's look at an example where we determine the concavity of this function. And that's the question. Is this function concave up or concave down at these 2 points? As soon as we are asked about concavity, this is a question about the second derivative, so we need to compute the second derivative. This first derivative would be 3x squared plus 6. That means your second derivative would be 6x plus 0. Then, to answer part A, is the function concave up or concave down at -5? We need to evaluate what is our second derivative at -5. So 6 times -5 is -30. Then we can answer it. A negative number is going to be concave down. A positive number is going to be concave up. So this is concave down. For part B, same process. What is the second derivative evaluated at 7? So this time we have 6 times 7. We get 42. That's a positive number, so we are concave up. So if you are given a point and you have to determine concavity, it's as simple as computing the second derivative and plugging that number into it. The next natural question would be, well, what happens if your second derivative is 0? 0 is not positive or negative, so what could we say about the concavity of a function? It's going to feel similar to what we talked about in the last section of notes. Anytime you have a point and the concavity of your function changes around the point, we would call it a point of inflection. One implication of that is that at the point, your second derivative will have to be 0 or undefined. This should feel very reminiscent of critical values. We had critical values when your first derivative was 0 or undefined. Here, what we have, if your second derivative is 0 or undefined, you have a potential point of inflection. Now, one application of why we talk about points of inflection would be when we talk about points of diminishing returns. So the context is that if you're looking at an investment, and specifically if you're looking at the rate of return of an investment, so your rate of return would be the first derivative, when the rate of return changes from increasing to decreasing, then we would say that this is the point of diminishing returns. So there's a good example of that in the book if you look at example 2 and 3 in the ebook. Visually, what does a point of inflection look like? So let's go ahead and put some dots on this graph to indicate where the graph has points of inflection. What you should be looking for is any place the function changes concavity. So if it goes from this bowl shape look that's facing up to a bowl shape look that's facing down, here the graph is concave up, here the graph is concave down, so the point where it changes, this point right here, is a point of inflection. Now that's not the only point of inflection on this graph, but that's like the very clear one that's happening. As you look at the right side of the graph, this looks like a downward facing bowl, and at some point it changes on the right, it looks kind of like part of an upward facing bowl. So we are concave down, followed by concave up. Somewhere in here it changes. So we'll just give it our best estimate. It looks like everything to the left of this point is a downward facing bowl. Everything to the right of that point is an upward facing bowl. So then that is also a point of inflection. With that in mind, we can look at the left side of the graph, and we can also identify a third point of inflection, because to the left it looks like it's downward facing, and to the right it looks like it's upward facing. So we had 3 points of inflection on this graph. Next, we want to talk about a second derivative test. Now, don't confuse this with what we were just talking about. We were just talking about finding points of inflection. Your second derivative test is used to classify extrema. This means it's used to find minimums and maximums. So the second derivative test can be used in place of the first derivative test if the question had asked us to find minimums and maximums of a function. So what do? First, we find the candidates for where this could potentially happen, and that's the critical points. We start with critical values. These are the x values where f prime is either equal to 0 or f prime is undefined. Pardon my spelling. After you have the x values, then you can find the critical points, which are x comma y, where the x value is your critical value. Once you have these are the candidates for the things that could be minimums or maximums of your function. Now, with the first derivative test, we made a sign chart of the first derivative in order to answer if they were minimums or maximums. What we do with the second derivative test instead is once you have your candidates, you compute the second derivative and you evaluate this at the critical values. So these were these x values. If your second derivative is less than 0, then the critical value that you produced is a maximum. Now, let's pause and think about why that would be true. Okay, we have a critical value over here. I'm going to just call it x, and let's say that the critical point is just a point up here. Now, in order for this to be a critical value, your first derivative would have to be 0. Now, as a technicality, yes, this could happen if your first derivative is undefined. However, we need the second derivative, so if your first derivative is undefined, you should never be trying to use the second derivative test anyway, because you won't be able to get any of these things. If the first derivative is undefined, the second derivative must also be undefined. So we really are focusing in on the first derivative being equal to 0. Okay, we know we have a horizontal tangent line, so what does the graph look like around that point? Well, if your first derivative is less than 0, you are concave down, so we can draw this concave down structure. If the bowl faces down and you have that horizontal tangent line, then by the very definition and nature of this arrangement, this looks like a maximum. So that's why we are calling it a maximum. Now, that may seem simple, but it's really easy to mess this up, because you have a second derivative that's less than 0. So, like, for example, let me just pick a number less than 0. You could have f prime of 3 is equal to negative 5. Okay, it's not intuitive to see a negative number and be like, ooh, negative means maximum. Negative means open down. Because you're opening down, that means maximum. Okay, in a similar manner, if your second derivative is positive, for example, let's say f prime of 3 is equal to a positive 7, then what does that mean your graph looks like? Well, over at 3, let's see, we have some kind of a point. We know that our first derivative equals 0, so we have a horizontal tangent line. Okay, your first derivative is positive. That means we open up. Let me draw in that upward-facing bowl shape. Okay, so then this looks like a minimum now. An upward-facing bowl is going to have a minimum at that value. Now, the second derivative test is not as good as the first derivative test. The first derivative test will always tell you if you have a maximum or a minimum, or it even identifies horizontal points of inflection. Your second derivative test can sometimes fail. If your second derivative equals 0, or if it's undefined, then the entire test is inconclusive. It doesn't mean that you have a minimum or a maximum, or that you don't have a minimum or a maximum. It just doesn't tell you anything. At that point, you have to go use the first derivative test. And if that's not clear what I mean when I say that, you draw a sign chart of your first derivative, you list all of your critical values, and then you have to test values to figure out if your first derivative is positive or negative or positive, right? And anytime your first derivative changes, that's when you have minimums or maximums. If your first derivative does not change, then no, there is not a minimum or a maximum at that value. So let's look at an example where we get to use the second derivative to understand a function. We would like to use the second derivative to determine the intervals on which the function is concave up, concave down, and we're going to locate the points of inflection. Now, I may be more picky than some people are. I would not call this a second derivative test. We are using the second derivative to determine intervals of concavity. This will allow us to find points of inflection, but I don't call it the second derivative test unless we are trying to find minimums and maximums. Okay, but maybe that's just me being picky with the vocabulary. We're using the second derivative, so let's find it. Your first derivative is 3x squared minus 18x. Your second derivative is 6x minus 18. We are going to set it equal to 0. So 6x minus 18 equals 0 means 6x is equal to 18, which means x is equal to 3. Okay, this thing, I boxed it in just by habit. What is this? This is a potential inflection point. Okay, what I have shown is absolutely not enough information to say that this is a point of inflection. In order to show that this is a point of inflection, you must show that your second derivative changes signs around this number. So then you would have to draw a sign chart, right? We list our potential candidate on the sign chart. This is a sign chart of your second derivative, so we want to very clearly label that this is a second derivative sign chart, not a first derivative sign chart. Okay, then we test values to the left of 3 and to the right of 3. So let me test some values. A number to the left of 3 is 0, a number to the right of 3 is, I'll pick 7, and then we need to evaluate these at the second derivative. So your second derivative evaluated at 0. If I plug in 0, I get negative 18. If I plug in 7, let's see, 7 times 6 is 42. 42 minus 18 is some positive number. Is it 24? Yeah, I think 24 sounds good. The point of what we are doing here is that we need to determine if this changes from positive to negative or negative to positive. Now, when I did a first derivative test, I would draw like, hey, this is a decreasing function, this is an increasing function. I'm absolutely not going to draw like a sketch of the function over this. The only thing that matters is we change from negative to positive or positive to negative. If it changes, yes, this is a point of inflection. Okay, so we have the x value of the point of inflection. So yes, there is an inflection when x equals 3. This is still not a point yet, so 3 comma something is our point of inflection. How do we find the y value associated with an x value? Well, we plug it in. And I will frequently ask my classes, where do we plug 3 in? You have 3 separate functions. Do you plug 3 into the second derivative, the first derivative, or the original function? Well, the answer is you can plug it in anywhere you want, but it tells you different things. If you plug it into the second derivative, it tells you your concavity. We would end up getting 0 and be like, oh yeah, there is no concavity here, so it's maybe a point of inflection. If you plug it in the first derivative, it will tell you if your function increases or decreases at 3. You can tell based on the graph. At 3, it looks like the graph is decreasing. That's not relevant information. If you plug it into the original function, though, it will tell you the y value of that, which is going to give us the y value here, which is the thing that we're looking for. Okay, so maybe that's like more information than we needed. F of 3 is equal to, let me pause the video and put this in a calculator. All right, I end up getting negative 54, which looks visually based on the graph like roughly the right spot. We have 3 comma negative 54, and I'll put that here, negative 54. This is our point of inflection. What you see on the sketch of the graph should confirm that this is a point of inflection. Everything to the left of this x value, the graph looks like a downward facing bull. Everything to the right of this value, the graph looks like an upward facing bull. All right, let's look at another type of question. We would like to find the relative minima, maxima, and points of inflection of the following graph, and then we're going to sketch the graph afterwards. So if you are asked about minimums, maximums, points of inflection, this is basically asking you for like everything you could say about the graph. Because it's asking about minimums and maximums, we're going to need to compute the first derivative, 3x squared minus 6x. Because it asks about points of inflection, we're going to need the second derivative. So I'm just going to compute them while I'm thinking about them. 6x minus 6. All right, we now need to be very organized with our work. Let's start by thinking about minimums and maximums. We are going to need critical values. That means your first derivative would be equal to 0. So 3x squared minus 6x equals 0. We factor that. 3x times x minus 2 is equal to 0. X is equal to 0 or 2. These are not minimums or maximums necessarily. These are places where minimums and maximums can occur. After we find these, we then come up with critical points. All right, so we need x, y values. We're going to plug the x coordinate we came up with into the function. So if I plug in 0, I should get 6. If I plug in 2, go ahead and do that in your calculator, but you should get 2 as well. So these are the candidates for minimums and maximums. Now, how do we know if they're minimums or maximums? We can either use a first derivative test or a second derivative test. Since I've already computed the second derivative, let's go ahead and use a second derivative test. Okay, for the second derivative test, you need to compute what is y double prime evaluated at 0 you also need to compute what is y double prime evaluated at 2. Well, this time I'm putting 0 into the second derivative. When you do that, what do we get? We get 6 times 0 minus 6 is negative 6. When we put 2 in, you get 6 times 2 minus 6. That's 12 minus 6. So that's a positive 6. Okay. This is enough information to tell you if this point is a minimum or a maximum. So let's write this down. Because, now I usually like to draw a tiny little sketch right here. We are thinking about just what does a negative second derivative mean? It means your graph should look like it's concave down. If the graph looks concave down, do you have a minimum or a maximum? We can say we have a maximum, max at 0, 6. Then we go and look at our second derivative evaluated at 2. When we put 2 in, we got a positive answer. So what does a positive second derivative look like? It means you would have an upward-facing parabola, or just an upward-facing bowl shape. So then that means you have a minimum at that point, so minimum at 2, 2. When you are able to use the second derivative test, it ends up being faster than doing the first derivative test, but if you feel more comfortable with the first derivative test, you are welcome to use that instead of the second derivative test. Okay, so this finishes out thinking about minimums and maximums. Next, let's go and think about points of inflection. Points of inflection happen when your second derivative is equal to 0. So let's find our potential points of inflection. Feel free to abbreviate that if you want. P.P.I, potential points of inflection. 6x minus 6 would have to be equal to 0. That means 6x is equal to 6, which means x is equal to 1. I don't know if that's a point of inflection or not. So what I'm going to do is I'm going to draw a sign chart. This is a sign chart of your second derivative, and I'm going to test values to the left of it and to the right of it. Now, because we have already been plugging numbers into my second derivative, what I am going to test, it's not going to be a shocker, I'm going to test x equals 0 and x equals 2, because I already know what I'm going to get. It's not f, it's y double prime is going to be negative 6, so we have negative numbers to the left of 1, and it's going to be positive 6, we have positive numbers to the right of 1. Okay, what does this tell us? If your second derivative changes from negative to positive, or if it had been positive followed by a negative, as long as it changes, yes, this is a point of inflection. All right, so we can say yes, 1 comma something is a point of inflection. What is the y value associated with 1? Well, in order to find that out, you would have to plug 1 into this function. So that would be 1 minus 3 is negative 2, plus 6 would be 4, so our y value is 4. We have finished almost all of this question. Last thing we would have to do is we would have to sketch a graph of it. Okay, so let's list the points. We have 0, the x values go up to 2, the y values start at 0, go 1, 2, 3, 4, 5, 6. So we have a point at 0, 6, a point at 1, 4, and a point at 2, 2. We know what these are. At 6, we should have a maximum, so the graph will go down on both sides around it. At 2, we should have a minimum, so the graph will go up around it. And here in between, it should look like the 0.14 is the halfway point between those two. So to the left, we're concave down. To the right, we are concave up. In this last example, we would like to categorize points on a graph based off of information about their first and second derivatives. Looking at part A, Suppose you know that the first derivative is greater than 0, and you also know that the second derivative is less than 0. Well, what would this tell you about the graph at this point? Your first derivative being greater than 0 means your function f is increasing, and your second derivative being less than 0 would mean that the function is concave down. Concave down. So we look for points where the function is increasing, like a, the function's increasing at h, and it also maybe looks like the function's increasing at I. Okay, g as well. So at a, g, h, and I, the function seems to be increasing. Where is it also concave down? So a is part of a concave down structure. G is part of a concave up structure. H, it's kind of difficult to tell. To the right, it looks concave down, and to the left, it looks concave up. So that's probably a point of inflection. It's not clearly just concave down all the way around. Okay, so then this means point A is the only candidate where we are increasing and also concave down. Let's look at part B. You need your first derivative to be less than 0. All right, being less than 0 means that your function is decreasing. F is decreasing. Your second derivative being greater than 0 means you are concave up. So the function would have to be decreasing. That happens at C, it happens at D, it happens at E. And you also want to be concave up. Well, at C, we are still concave down. At D, we're halfway between being concave down and being concave up. So that sounds like a point of inflection. And at E, we are concave up. Okay, decreasing, concave up, E is the only candidate. Let's look at part C. What if your first derivative is 0? If the first derivative is 0, you have a horizontal tangent. Okay, there's 3 ways that you can have horizontal tangents. You could either be looking at a maximum, a minimum, or a horizontal point of inflection. So it looks a little bit like a shelf over there. Now, we know more information than just that. We also know that the function's second derivative is less than 0, meaning we are concave down. Okay, well with that, to have a horizontal tangent and be concave down, the only candidate that meets those 2 conditions is B. When you look down at F, you are horizontal tangent, but you have a concave up structure. At I, you have a horizontal tangent, but you are not concave up or concave down. It's actually a point of inflection because we're changing right there. So we will say that our answer has to be B. Last part here, what if your first derivative was less than 0? So that means the function is decreasing. And your second derivative equals 0. So the second derivative being equal to 0 means that this is a potential inflection. Based on a graph, the implication is it's probably a point of inflection. So can we find a place where the function is decreasing? It decreases from B all the way down to F. That also looks like an inflection point. So C is not inflecting, it's concave down all around C. D looks like inflection. We changed from being concave down to being concave up, so that looks like the best candidate so far. E, it's clearly part of a concave up structure, so let's go with D. We are decreasing, and we are also a point of inflection. And you can pick on any of these points over here. So we've specifically focused on A, E, B, and D, but let's pick on something that wasn't one of the answers over here and list what the first derivative would be and what the second derivative would be. So let's do this. At H, your first derivative, let's see, what is the first derivative doing? If the function is increasing, your first derivative would have to be positive, so it's greater than 0. And your second derivative, let's look at it. Right here, to the right, we are concave down. To the left, we are concave up, so that's a point of inflection. So your second derivative equals 0. Now let's also pick on I, and then we can be done with this example. At I, your first derivative and your second derivative, let's see, what do we know about these? It looks like we have a horizontal tangent line. A horizontal tangent line means your first derivative will equal 0. It also looks like a point of inflection because we are concave up on the right, we are concave down on the left. So this is the type of behavior you would expect to see if your first derivative and second derivative were both equal to 0. Well, that does finish these notes, so I hope that you've found them helpful in thinking about concavity and points of inflection.